Welcome to the course Algorithmic Design. Session 2, Fundamentals. That's part of this sort of five big sort of parts that we have: fundamentals, continuous models, discrete models, optimization, and learning. I decided to start with a quote. Actually, this quote was somewhere else in the presentation first, but then I decided to put it at the very beginning because it was the only one, and it in a way refers to the whole to basically the whole lecture. So it's a quote by Richard Hamming. He also, who's an American mathematician and worked in computer engineering and telecommunications. He, for example, discovered so-called Hamming. Well, actually, I guess it's invented. He invented this so-called Hamming code or Hamming encoding, which is used for example, when you work with text, and he said that the purpose of computing is insight, not numbers. Or so somehow this idea that computation or computer science, of course, from his field, has little to do with computers in a sense that same as in being a surgeon is not really about using scalpels and knives, or in that sense, also computer engineering or computer science is not really about computers. It's about something that is more fundamental. And of course, this was his perspective because he was a mathematician. So yeah, but of course, we work a lot with numbers, and computers are very convenient machines for doing calculations. Okay, and this is, I think, maybe the only other slide where I have sort of text. No, actually I have one more, but I started a bit, I have this compilation that I did for my textbook, which is kind of a summarized development of important concepts and their inventors leading to the development of computational design in the 21st century. So it's not really historical development of computing, but it is sort of, yeah, it is kind of a summarization of concepts that basically build up slowly and led us basically to today, to the digital age. But they also directly relate to kind of computational design and basically, in that sense, digital design in the 21st century. And here I listed them. It looks almost like they're listed alphabetically, but this is just an accident. I didn't put years here. So just kind of the inventors. Also, we have ancient Babylonians, in a way, maybe the earliest users of numerology. Of course, I'm not a historian, so you can always challenge me here. The development of numerology, in a way, use of numbers to discern patterns, and of course use it then for example, for figuring out the patterns for solar eclipses and tides, and so kind of seasonal changes. And in a way, Greeks did something similar, but they employed sort of reductionism, meaning they kind of understood that it's not only about patterns in numbers. It's not, the Pythagorean theorem is not really fundamental if you look at it in the context of Euclidean axioms. So there is something that is more fundamental in geometry than, for example, Pythagorean theorem or the axioms of Euclid, the five postulates, and then in that sense, kind of development of geometry. And this basically, well, we are still using this sort of principles today. Also, our at least Euclidean geometry is based on Euclid's postulates, and not on anything that kind of Babylonians invented. Or okay, then we have Aristotle there, kind of invention of propositional logic, which is not really, well, it's a very early precursor to computer code, or because it's propositional logic is some form of formal language. Or so we have natural languages, and then we have formal languages. Propositional logic is one form of that kind of formal language, or so it's kind of something between maths and language. Or we have ancient Hindus to thank for positional decimal numeral system. So there's a reason why Romans were culturally very influential, of course, in at least the western part of the world, but you don't hear of any famous Roman mathematicians. And engineers, yes, but not mathematicians. And the reason is because, try to multiply something using Roman numerals. Or so it was basically the kind of positional decimal numeral system, and of course later the Arabic numerals that we are using today. Also the invention of the zero. It's very crucial. So Romans didn't have zero, and we got that from the Indians. Then Al-Khwarizmi invention sort of algebra, in a way looking at math not just about numbers but about symbols. So we go a bit more toward sort of general or generalization, or so math is kind of more general than just numbers. And then here I put in Alberti, so that's going to be next slide. In a way, invention of digital maps, even though they didn't really influence the development later. So that's kind of just a sort of historical idiosyncraticity, or kind of a curiosity that Alberti basically was already thinking about, in a way, digital storage of visual information, at least maps, before the invention of computers. And of course, he's very important in general for architects. Then Leibniz, binary arithmetic. So our computers are work with binary numbers. That's it. Then Boole, George Boole, Boole's logic. So Boolean logic. So I'll show you some of the concepts that derive from there. And of course, last week I showed you Boolean operations and Boolean value variables. So kind of this is basically Boole's logic, and also the kind of Boolean algebra, or that is used. That is kind of this bridge between sort of binary arithmetic in a way and kind of computation. Then Charles Babbage, differential machine, kind of the first mechanical computer, even though it was a bit specialized. So today's computers are not really predecessors of, or they're not how do you say it? Today's computers are not really they didn't really develop directly from the differential machine, because that differential machine was very this analytical engine was very specialized. So in a way, computers had to be completely reinvented at the beginning of the 20th century. But that was, in that sense, maybe the first time something like that was tried, even though Leibniz, of course, was already thinking about machines that can compute, but he never really built anything, or it was Babbage who built. And then Ada Lovelace, of course, not the first female programmer, but the first programmer ever, or so in a way, invention of computer code, of course, directly for the differential machine. So we credit her today as the first programmer. Turing, in a way, the groundbreaking paper on the kind of what is computable, or so here I didn't put Kurt Gödel and his undecidability, for example, theorem, but kind of Turing answered directly to this or to these problems that kind of arise after Gödel, and his paper was specifically to this kind of Hilbert's sort of Entscheidungsproblem, or so the sort of halting problem of computers are. But kind of Turing in his seminal paper sort of described how you could build this or how you should conceive this universal computing machine in this so-called today. So today we call it the Turing machine. They can, anything that is computable can be computed with the Turing machine. And today's computers are Turing complete, or so they can compute anything that can be computed with the Turing machine or with today's computer. So yeah, that was kind of the first theoretical paper, and that's what really distinguishes, let's say, today's computers from the differential engine that Babbage built, because differential engine was not a universal computing machine, or the Turing's model was, and it was, of course, then later, just a little bit later, Shannon. So Claude Shannon, the father of information theory, who kind of created the digital version of this then universal machine. So kind of the or conceived that basically the digital circuits can be basically used, or you can build kind of Boolean gates or logic gates using digital circuits, and you can basically built Turing's universal machine. And then it was John von Neumann, who basically kind of conceived the so-called von Neumann computer architecture, which is basically all computers today, except quantum computers, of course, but all computers today they have von Neumann architecture. So they have the CPU, the central processing unit, they have digital storage of both information and instructions. So before that, instructions were kind of maybe on punch cards, and so there was a kind of a difference between instructions on a computer and the data that computer was working with. And von Neumann just realized, no, this should actually be the same thing, because this is all just information. Instructions are as well just information, and that's in a way this synthesis that sort of happened over kind of Boolean logic, binary arithmetic, Turing universal machine, the digital circuitry, kind of all came together, and basically the modern computers were built. And there were some other, let's say, computers that were developed in the UK and in Germany, but basically ENIAC was built by von Neumann, was basically kind of the first, let's say, the first predecessor of the modern computers. Also, von Neumann is credited, so I don't want to bore you too much with this history, but von Neumann, after the Second World War, so after the Manhattan Project, when the ENIAC, the first computer, was used to calculate, do calculations for example, the atomic bomb, he released all the details of the ENIAC construction. So he just kind of published published papers on it. So they became, companies could actually build up on that. And there were some other predecessors, for example, in the UK that Turing worked on, which were still classified all the way until 50s or 60s or so. They didn't serve as, they couldn't really kind of inspire or sort of help develop the digital age, because they were military secrets. And von Neumann kind of understood that computers are important, and they should, now the war is over, we have to kind of start building computers. And that's why kind of, IBM and Microsoft and so on developed in USA, not in UK. Okay, even though UK had, of course, great universities like Cambridge, Oxford, and so on. Okay, so that's the bit early 20th century, and from then on, it's just smooth sailing. Okay, and now certain concepts. So I think these pictures I already showed last time. So this idea that in a computer, everything is stored in a digital way, and we can basically store also not just text and numbers, but basically these numbers, if we have a certain convention how we of course array them, in this case a 2D grid, we can store images, and Alberti was already thinking about that, basically storing sort of visual information, or at least spatial information, as a computer code. Or so these two ideas are basically in play today. Also, when we work with computer data, also just when we work with computer languages like Python, we will use arrays, one-dimensional and two-dimensional arrays, and we always have to think of them a little bit like this. Or so it's just a table of numbers. It's like an Excel sheet. Or that's the idea. That's how we can kind of basically represent visual information. And here I have some references from, this is from old book from Ludger Hoverstadt, but he's referencing even some of the earlier kind of CAD work, or so methods for editing and manipulating geometry, or they depend on the digital representation. Or so it's unfortunately very small. I apologize for that, but you can take a PDF and sort of zoom it a bit. We can represent geometry as kind of wireframes, or as different projections like plan sections and so on. We can represent them as surfaces or as volumes, and depending on how we represent these three-dimensional objects, we can then do different things with them. And that leads us a little bit, from this idea of that we have a drawing, which is basically a collection of some projections of a three-dimensional object, to the actual three-dimensional object, which can maybe also be a physical object, but in a computer, it is a three-dimensional model. To the idea that not even that is enough. Also, if you look at, for example, how BIM works today, so building information models, it's not just geometry that is stored. You have tons of other information like, materials, maybe some sequence of construction, or which element has to be placed first. That's also encoded inside. So geometry of the material, but also maybe color, or maybe if you have different types of materials, like for example different concrete types, you can put that information also in the digital model. So in a way, it's not only just geometry, you get almost like a hyper model. That kind of describes your building or your three-dimensional object. Or so we really work with this sort of multi-dimensional kind of layered data. Okay, and then this now kind of shows this idea that we can encode information, or so we can encode information. We can encode spatial information using either lists, arrays, or kind of grids, or so sort of multi-dimensional arrays. So this is one early example from Lionel March, 1972, of kind of using a hexadecimal code. Again, I apologize, this is very small, but again, in the PDF you can zoom in. You can use a hexadecimal code to basically represent like a small 3D voxel canvas, and he used this to basically represent the model of this Seagram building, or from Miss van der Rohe. So in a way, you have a hexadecimal code which translates directly to a volumetric model. Of course, nature uses also information encoding, so DNA is nothing else but just a code. Or so we have the four DNA codons, or so A, U, G, and C, and basically they encode proteins, or they encode amino acids, and these amino acids then translate into, or some of them translate into proteins, and yeah, and then basically the proteins are nothing; they're just composed from these sort of sequences of amino acids, which then fold. Also, we can go from sort of sequential information into quite complex sort of molecular machinery, and of course, many things. Well, the cell is dependent on that. Okay, and then this kind of whole idea of an algorithm, or we can have an object. This is actually from a book from Mark Burry, who is an architect and computational designer originally from New Zealand, but now, of course, in Australia. Is also working on the lead architect on Sagrada Familia renovation in Barcelona. So he wrote this kind of nice book where he explains some of these concepts. So this from his book. There's kind of an algorithm, and then there's this sort of a design, or on the left. So the design is in a way manifestation, or some kind of geometrical manifestation of that code. Not even sure which computer language this is, but maybe Java, but I'm not sure. Okay, and this is also, again, now 30 years old reference. This idea that when we use code to describe geometry or design, we basically have to make this design explicit. Also, we have to basically be we cannot be approximate anymore. Also, we have to really kind of define how the things look like and why do they look like, like that. So this you can basically call explicit design. Also, this is sort of this is like sort of a small or short conditional statements that basically that can guide you to sort of to kind of design the building. Also, if the site is in cool climate, then design partially underground massing and enable snow accumulation to stand against walls or on roofs, and enable internal heat zoning with airlocks at entryways. Also, you can kind of create you create this sort of explicit sort of instructions. Sometimes they're also called expert programming, or expert systems. So it's like a code that basically contains certain expert information. Also, how should the building look like given certain conditions, and you can use that then to derive your shape. And of course, if you're able to describe the design in this way, then you can also generate with the code, with the computer. If you're not able to create this code, or this embed this expert information into code, then you have a problem. Also, then you cannot really actualize it through code. So the computer basically doesn't know what to do. So this way of making your design explicit is basically essential to computational design. And not to go too much into it, but you can imagine that the way architects and general designers design very often is a result of a bit of an obscure process, and many architects like to keep that process also obscure. You know, they would design something, and or similar maybe with artists, and you would ask them, how did you come to this? And they would say, oh, it was, you know, somehow it came to me, you know, in a dream, or I did a small croquis or something, or croquis kind of a sketch, and this is what came out. Or so they like to make the process a bit obscure, and of course that's yeah, so that's in a way the opposite of explicit design, let's say. Okay, but again, if we are able to make this design explicit, so kind of describe these parameters that are guiding our decisions, then we can write code, and then we can profit from the fact that, you know, a code can sort of, we can just generate multiple variations by changing parameters that we put in. Or so that way we work in this paradigm of parametric design where parameters are explicit and they are controllable, or so I can kind of array them around. And today, depending on the time, I will try maybe to do, of course, a small example of this already. So do kind of small array grid of elements, let's say. Okay, a little bit back to color. So there's actually a great reference that I forgot to again include in the presentation. There's a book called The Atlas of Digital Architecture, which just came last year out, and there they give kind of sort of advice to young architects, and one of the advices that they give is do go into math. Or so actually it turns out the more math you know, the you're going to be a better computational designer, because somehow everything can be underlying principles are basically math. And this is a great example. So when we talk about color in the digital realm, yes, you know, we can talk about this additive or emission color model like RGB, where we have red, green, and blue primary colors in light, or so they are basically light colors, or they're just light. And we can mix these lights together, and we get these secondary colors, and that's basically how color on your screen is created. Also, everything that shines, so computer screens, monitors, mobile phones. So mobile phone screens, they all work. They all use this principle to mix light colors. So these are then specifically maybe LEDs, which have these three components, and they mix in different proportions, and we basically get all the other colors. Not all of them, but a lot of other colors we can get in this way. And then, because we have three components, we can almost think of a color space. Or so in Photoshop, when you're selecting color, you have sort of a section of color space, and then you can move through these sections, and that's how you basically choose a point in this space. Or so it's in a way a color space, and every point in this cube is some color in this RGB model. And the same works with CMYK, so which is this absorption or subtractive color model, where you have cyan, magenta, yellow, and then you add additionally this key, which is basically black. So when these three mix, they kind of, you get black, but it's a bit off black. It's not really nice black, so you can add extra a black to get this darker tone. And this is so this you use for printing, or so everything that is printed on paper. So the light is reflected of the pigments, and the pigments absorb all the wavelengths except the ones that you see, and that's why when they mix, you get actually darker tones. And again, in computer, you can actually also work with this color model, even though this one is basically used only for printing. And there are some other color models as well. But basically, again, we would have a color space. Yeah, we would have kind of a color space, and every point in that color space is then one color that we can use. Also, it's in a way, even color becomes mathematical in this sense, or this sense, or geometric. Or for example, in RGB, all the grayscale values are on this big diagonal. Or so when all the numbers are the same and all of these components have the same number, we get grayscale value. That's why when you look at the RGB code, and if all the numbers that are the same, you know it's some gray. Or so it's in a way, it's almost mathematical how you can kind of read color without really perceiving it. Okay, so that's color. Of course, I showed you some example before in raster graphics where we have pixel, but we will in Rhino and in our work primarily work with vector graphics. Or so we have some shapes, polygons. So we start from points, lines, polylines, and then the curves, NURBS, curves, surfaces, and even kind of volumes. They're all described through vector operations. So the vector is the basis. We have sort of points. We use vectors to translate those points, but even points can be represented. They can be represented through vectors. Or a point is just a translation of the origin for the point vector. Or so that's why in Python the notation for points and vectors is actually the same, even though mathematically they are different things. But the notation is exactly the same. So you can use them sometimes interchangeably. And when you have this sort of, let's say, mathematical or basically linear algebra understanding of shapes, then you can use linear algebra like matrices as transformations to transform this geometry. So all the transformations of this geometry can be described through some matrices. This is specifically right here. This is a transformation matrix. Or so it's 4x4. Here we have rotation. Here we have translation. And I think this bottom row is always empty. Just zeros, but we need to have kind of 4x4, so we can do matrix multiplication. So composing of transformations. I mean, it's easier if you have a square matrix. Okay, but we will not really go this much into math also, but we will work with sort of vectors. And again, these matrices are these vectors. They're basically just some kind of arrays. Or in a computer, these are represented as arrays. So it's just an array of numbers. And you can imagine there's a computer memory, and there are sort of slots, and these slots are basically these cells. Or so when we work with, for example, Python, we are going to talk about lists or arrays. And again, they can be one-dimensional, two-dimensional. And these are examples from NumPy. So we will not be using NumPy. We actually cannot use NumPy in Rhino, unfortunately, because Rhino is actually Iron Python, but in Google Colab we could use NumPy. NumPy is it's a library for Python to really efficiently work with huge arrays. So, but this we would use, for example, if when you work with maybe machine learning applications or data analysis, or like large if you work with in kind of sort of data science and with kind of large files and so on, then you would use NumPy. So in Rhino we cannot directly use it, but here I'm just showing you some examples. Also, in a way, there's somehow connection between operations in linear algebra, with matrices, and these sort of arrays that are basically kind of programming arrays. So they're kind of, this is data. This is basically how data is stored in a computer. Also, if you have a bit of background there, you can actually perform things. You can then do many things. Also, that's basically your data is in this form. So if you think about when we talk about, for example, Photoshop and filters in Photoshop, when we do like contrast adjustment in Photoshop, basically there's some operation being performed on these huge arrays, which are maybe two-dimensional or actually multi-dimensional arrays. In terms of if you have colored images, so RGB images in Photoshop, there are some operations performed in these large arrays. They are very mathematical, but their outcomes are, of course, visual. So in Photoshop, you don't really see the math, but you see the outcome. Or okay, and this way of sort of thinking, or this sort of this way of working, where we have just kind of lists or these arrays, and then we perform operations on them. This is a little bit how Grasshopper works. So that's this so-called flow-based programming. Or so in a way, you have just components which are functions, and you have data which is somehow in some list form, some array forms. In Grasshopper, if you know, you have the these trees, and basically you have lists and you pass them through these functions, and they get transformed, or so you can merge them together differently depending on what the function is doing, and you go in a way this graph, you go kind of from left to right, and basically you're just transforming arrays. And then the question is, what are these arrays? They might be a list of points, they might be a list of some objects or lines or shapes or whatever. You're kind of employing this type of thinking. Or so you have arrays and you just transform them and you get some results. And again, when you work in Grasshopper, this is becomes very straightforward. But we will not work in Grasshopper directly. We will be working with Python. So we are going to work a little bit differently. So we'll work in an object-oriented way. So basically, we still work with lists, but our lists are now objects, and we can also create sort of classes, or custom objects, or we can define a class. I think I also explained this a little bit last time. We can create a class, which is sort of a prototype object, and then we can, from this class, we can create instances, so specific instances of that class, which are going to be specific objects that we can use. And these will be points, there'll be shapes, later there'll be particles. When we work with Cellular automata, there'll be kind of cells. They can basically, these objects can then represent elements that we used in design. And these objects themselves, I mean, you can think of, they're just static in memory. I mean, they're stored somewhere in memory. They're also somehow, in a way, some kind of lists or containers, and but they can communicate with each other, or we can make them kind of talk to each other, and they can exchange information. And by doing this, they can perform calculation, or so that's basically how computation is done. They exchange information and they compute something. And again, I will show you later when we work, for example, with particle models, like you want to simulate, for example, swarming of particles. Then every particle or every void or every kind of a swarm element will be one object, and this object will have attributes like position, velocity, maybe some other things. And then depending on the velocity in every iteration, its position will change. And if there are some forces acting between different particles, then the particle or the object will always check what is the other object that is close to it, and it will start exchanging information, adjust its velocity or path, and so on. So basically, we will adopt this object-oriented way of thinking, where basically we will try to split everything into objects, and then just make these objects sort of communicate with each other. We'll use it to store information, but also to perform operations. I apologize also if this is very abstract now at this moment, but that's just a little bit of background that we have to go through. And of course, I'm maybe not the best person to explain this because I'm not a computer scientist, but yeah, maybe some of these things will become a little bit clearer later. Okay, so this is, for example, this on the top. It says here, this is a diagram that shows 3 classes. Or so when we talk about object-oriented programming, talk about we can define a class, and these are basically 3 classes. There's a class rectangle, class circle, class shape, and then this class rectangle can become a specific object. It can become a specific rectangle if we give it length, breadth, or I guess this is width, and maybe an origin point, and then we get a specific rectangle. But we can have different rectangles as well. So this class just defines what the rectangle needs to, what is the information that the rectangle needs to have in order that we can define it well. Or same thing with circle. The circle needs only 2 pieces of information. It needs a center point, and it needs radius. And if you have these 2, which are very kind of simple, one is a point, the other one is just a number, we can draw a circle. Then we can pass this object through a function where we say, okay, give me your center point, great, give me your radius, and now I can draw this circle. So we can then tell Rhino, based on this object, now draw me a circle. Or so the Rhino is basically using the information that is stored in the object to draw a circle. And here, what this diagram showed is that these are we have a class rectangle and class circle, and in a way, they can also form another more abstract class called shape. So because both of these are shapes, so they can kind of in this would be called kind of inheritance, or so we would have a higher class or more abstract class called shape, from which we can derive different shapes, rectangles, circles, maybe points, lines, and so on. Also, but basically each of these is a kind of a class, and we can define objects through this. And here, this one a little bit goes. This one shows a little bit kind of the same thing. This would be an object. These boxes would be objects, and in this this picture, the point is that these objects can communicate with each other, or so they can exchange information, and that's actually how computation is done. That's how kind of interesting things are happening. Okay, so that's the best I can do. Okay, but maybe a little bit here, so to get a bit more to concrete things. Also, this is specifically Python code, which we'll work with. These all show different types of program flow. Or so this is how you can write kind of a Python code where you define two functions. You define function get name, define function get age, and then this is where the kind of program execution starts. Or so that's why here we have start, and we execute this get name, then get age, and then there's some kind of output. Or so here we first have a definition of functions, and then we have execution that happens here. This diagram here shows if then else flow diagram. Or so these are these conditional statements that I showed last time. So we can have, based on certain conditions, we can decide which way to branch computer code execution. Or so we can say, if something is true, do this. If something else is true, do something else. Or so we can basically, this is how we make these decisions. And these two on the right, this is basically, these are loops. Or so we can repeat certain things multiple times, and loops are very useful there. Or so we can kind of, if you have some operation where we have repetition, so it's the same instruction, but maybe different information that we need, we can use loops in order to execute these parts of code. Or so, yeah, in that way, repetition can be automated in this program flow. Or so we don't need to write things multiple times, but we can just say, okay, repeat over and over something. Okay, and then all these parts, they can come in together into basically a computer program if it pairs also with data types and so on. Okay, and now this is now already kind of slowly end of the presentation. This is a bit maybe abstract now, but I mentioned before that George Boole defined these. He defined Boolean operations or Boolean algebra, and then if you're an architect or designer, you very often use these so-called Venn diagrams. Or so you have a Venn diagram where you're showing you have maybe two areas or two shapes, and you can sort of add the shapes together. You can add them together, you can subtract them, you can calculate their difference, and certain other operations here. And these are basically all Boolean operations. We call them kind of Boolean operations. They're also related to logic gates, so specifically how your computer is built in kind of on electronic level. And this is great if you're a computer scientist or a mathematician. You think about kind of logic operations. You can kind of create formalize and also calculate with them, which we will also use in some parts. So at one moment, we will define maybe a conditional statement. And then we will say, for example, if a shape has this size and it's bigger than this, but smaller than this, and if it's an edge of the square, but not on this side, then you do this. Or so when we describe something like this, we are defining a conditional statement, and we are in a way constructing our statement using these Boolean operations. But also when you work with, in general, just in modeling, like for example in Rhino, there are these Boolean operations on shapes. Or so we can, for example, create a shape like this by using more primitive shapes and using kind of Boolean operations on them. Or so you have this cylinder here, this one here, and we can join them. Or so we can create a union. This is a sign for union. We get like a cross like this, okay? And then we add another cylinder in this direction. We join these two, and we get like, yeah, what is this? Like some kind of instead of cross, it's some kind of a frame. Then we can do another shape, which is like a cube and a circle, or sorry, this is a sphere, and then here we can do a difference, or so we kind of subtract the sphere from a cube, and we get kind of a sphere, cube with rounded edges. And then we take these two and we sort of subtract them, or so we subtract this this one from this one here, and we get basically a shape that is like this. Also, this is basically defining Boolean operations on shapes. So we can add them together, we can subtract them, we can calculate their sort of difference. And this is used specifically for, this is called constructive solid geometry. It's also very useful if you're a mechanical engineer, because very often these operations that we are doing, they correspond, for example, to a certain machine that you would use in order to build these shapes. So in a way, you have correspondence between how you model and which maybe machine you use. So you can have a very complex shape here, but you know exactly which steps you need to take in order to produce maybe an element like this, or to do a modeling. Okay, and this is basically how you can kind of create three-dimensional objects in, well, in Rhino, Blender, I guess AutoCAD as well, or wherever, whichever software you want to use. Okay, this is actually more or less the last part of the presentation. This whole lecture now that I did, the whole point of the lecture a little bit is, when I say fundamentals, I sort of meant really fundamentals of computation. And when we talk about computation, we talk about computation models. And again, this is concurrent. I forgot to put in functional computation models, concurrent computational models. So we really talk about models of computation, and basically there are three big groups of computation models, so-called sequential, functional, and concurrent. Concurrent just means kind of parallel, where things happen in parallel. And we'll be looking in this. So in this course, we'll be looking at basically only two of these. We'll be looking at cellular automation, and we'll be looking at actor models, or sometimes kind of agent-based modeling, you can call it like that. For example, abstract rewriting systems are shape grammars, which we will not really look into this course, even though they are kind of a topic. And I mentioned before kind of Turing machines. Just as reference, for example, finite state machines, every time you go to turnstile, so there are no turnstiles really in Finland, but maybe if you go to London, there's this this machine that kind of lets you into a metro station. That's a turnstile. That's a kind of finite state machine. When you have maybe a simple machine that sells you drinks, maybe have a machine on a station and you put in a coin and you get the drink, that's also a finite state machine. Also, all of these correspond to some there are some kind of ways to compute things. And again, in the next lectures, we will be looking at basically cellular automation, because it's very versatile, kind of relatively easy to build up and useful for us, and agent-based modeling, which builds a little bit on that as well. So we'll be looking mostly at these concurrent models. And this is the example. So game of life, so Conway's game of life, example of cellular automation, which is sort of very nice and playful, but we'll be doing some other stuff as well. Sometimes it's called the actor model. We will be calling it agent-based modeling, where we can, for example, simulate different particles. So in a way, if you would, for example, simulate fluids or kind of particles, or for example, we'll also work with dynamic relaxation. We will simulate relaxation of membranes. There, every node in a membrane will be one particle. It will be connected to other nodes through kind of simulated springs, and we will basically be simulating a membrane, or in this case, these are just molecules which are sort of freely floating. And the difference between these two, they're kind of similar, but the cellular automation is a discrete model. Also, we have cells. We have cells which are sort of fixed, and these cells have certain states. So it's a little bit like your computer monitor. And in this actor model, these are sort of discrete quantities which can move around freely. Also, they can freely move in some kind of volume or space. Okay, so in the later lectures we'll be using. I'll show you basically how to do both of these in Rhino and in Python. And that's when the things are going to get complicated. That's why we'll take a bit of time until we get there, so that I don't overwhelm you. Okay, and this is sort of the some examples that I will show you today. That's why I put it here at the very last. There's this concept of randomness, or so that we will be using randomly generated numbers in our code all the time. Basically, random numbers are our way to simulate naturally occurring processes. So to simulate non-determinism in a computer, which is essentially a deterministic machine. So basically, when I say random generation, that means a computer will give us a series of random numbers, meaning accidental numbers are. So these numbers are here random. And this we can then use to, these numbers sometimes we'll get them as pure numbers, and then of course we can translate them into shapes. In this case, this is an example from Michael Knoll, 1965, called Composition with Lines. So it's basically kind of, it was like computer coded Mondrian pictures or Mondrian paintings, and it uses different degrees of randomness to create these sort of effects. And maybe today we'll do maybe a simple example that we can do something similar to this. Then, not to become too technical, but there's a difference between kind of complete randomness and sort of pseudo randomness, or in this case, this is called actually quasi randomness, meaning you can vary the degree of order, or so. And this you can then do depending on if you want to create certain effects. So here, for example, you have a lot more, you have like a more uniform distribution of points. And here you have kind of sort of complete randomness, or so the point can appear anywhere within this box. And again, in Rhino, in Python, this is very easy to do. So this is maybe one example that we will do today. Maybe code a few of these. And we'll probably end today or come today to the so-called Brownian motion. Or so, Albert Einstein got the Nobel Prize for discovery of or explanation of a photoelectric effect, and for mathematical explanation of Brownian motion. So basically, how molecules move or particles move when they're hit by kind of molecules that are agitated by heat. Or so he described how to calculate, the sort of in a probabilistic way the trajectories of these particles, and then that's how he got his Nobel Prize, not for theory of relativity, but basically we will be today we will also connect this sort of idea of randomness and just kind of try to do this random walk as well, and we can get some funky looking sort of folded lines in Rhino. So this is also rather easy to do, and so we'll try to do that today. And yeah, the randomness is it's a big topic, which again we will not go super into, but this is one interesting example. So there are different ways to generate random numbers in a computer, and they are in a way deterministic, but they have a chaotic nature, so a periodic sort of nature. And one of them is a cellular automata model called Rule 30, discovered by I forgot what his first name is, but we call him Wolfram. So that's the guy who owns the webpage Wolfram Alpha also. So he classified these 1D cellular automata rules, and he discovered that some of them, for example, this Rule 30, can be used to generate random, or they're basically pseudo-random numbers. So you can create these different patterns, and these examples we will do in one of the later sessions when we go into cellular automata. And yeah, it turns out that nature is using, seems like using similar patterning to create at least some patterns on some organisms. So this, for example, this conus textile shell, or has basically pattern on it that is very, very similar to this Rule 30. Or so this is generated on a computer, and this is like a drawing of this shell that you can find in the sea. Yeah, so some of these patterns also then appear in nature, which is, I think, quite remarkable. I promised that I will always give you some references to read, which are sort of, let's say, loosely related to the topic of the day. And So in our collection of texts, there are 2 texts, which I would just recommend you to read. It's not compulsory, but maybe a suggestion. So the first one is The Logic of Architecture, Design, Computation, and Cognition by William J. Mitchell from 1986. Or so it's already quite some old text, but it has a lot of good kind of historical references. So kind of has that perspective, and then a little bit later one from Peter Eisenman, Architecture After the Age of Printing. So it introduces this, basically develops this idea of the Eisenman had of deconstructivism, which is already kind of, again, 30, 40 years old sort of idea, or sort of a philosophical, let's say, thinking in the architectural discourse. But in the 90s, these texts, actually there were 2 essays that were done by Eisenman that became quite influential for the and this, let's say, the digital discourse of the architects. Also, this kind of introduction of the fold, this Deleuze's idea of kind of the fold, and some, how this deconstruction kind of falls into fed really well into this sort of parametricism styles of kind of Zahadin and Patrick Schumacher that came later, of course. This is sort of a very good maybe text as a reference from those times. So those are these kind of early digital styles. Or and yeah, Peter Eisenman is a great, good architect, but also a very good writer. So I would always recommend you to have a chance to read him.